Imagine leaving a cup of hot tea on a table. You don't need to touch it. You don't need to watch it closely. You already know what will happen. The tea will cool down. But the reverse never happens. The room will never suddenly grow cold while the tea reheats itself. This simple, everyday observation hides one of the deepest laws of physics. A law so fundamental that it applies to stars, engines, atoms, black holes, and even the entire universe. That law is the second law of thermodynamics. It tells us that something called entropy always increases, and once entropy is created, it can never be destroyed. Not by technology, not by intelligence, not even by perfect engineering. This is not a limitation of humans, it is a limitation of reality itself. Why this law is so strange? Most laws of physics are reversible. If you film two planets orbiting each other, you can run the video backward. The motion still obeys Newton's laws. If you reverse the equations of electromagnetism, they still work. Even quantum mechanics allows time reversal symmetry. But entropy is different. It introduces a direction into physics, a before and an after. A reason why ice melts but does not unmelt. Smoke spreads but does not regather. Glass shatters but never reassembles itself. Entropy gives time an arrow, and this arrow never points backward. The central question. So the question we are really asking is, why does the universe keep track of entropy so strictly? Why can't entropy be erased, removed, or undone? To answer this, we must first understand what entropy actually is, and why the common explanation of disorder is deeply misleading. Most people are told that entropy is disorder. This is not wrong, but it is dangerously incomplete. Because disorder is subjective. Physics is not. To understand entropy properly, we must go beneath what we see. Macrostates versus microstates. Consider a box filled with gas. From the outside, we describe it using just a few quantities: temperature, pressure, volume. This description is called a macrostate. But inside that box are billions upon billions of particles with a position, a velocity, a direction. Each exact arrangement of these particles is a microstate. Here's the key idea. Entropy measures how many microstates correspond to the same macrostate. The more microscopic ways a system can exist while looking the same to us, the higher its entropy. Why high entropy states dominate reality? Low entropy states are special. They require precise arrangements, highly constrained motion, and unlikely coordination between particles. High entropy states are easy. They allow many arrangements, random motion, freedom at the microscopic level. So when a system evolves naturally, it almost always moves towards states that can be realized in more ways. This is not a preference, it is not intention, it is overwhelming probability. Ludwig Boltzmann, the man who understood entropy. This insight was first understood deeply by Ludwig Boltzmann in the late 19th century. Boltzmann realized that entropy is not a mystical force. It is statistics applied to atoms. He wrote the most famous equation of entropy. S equals K ln W, where S is entropy, W is the number of microstates, K is Boltzmann's constant. This equation is engraved on Boltzmann's tombstone. It summarizes his life's work and his tragedy. Boltzmann was ridiculed in his time because many physicists did not yet believe atoms were real. Today, his idea is considered one of the deepest insights in science. Entropy is not about chaos, it is about counting. A shuffled deck of cards has high entropy not because it is messy, but because there are astronomically many ways it can be shuffled. A perfectly ordered deck has low entropy because there are very few ways it can exist in that exact order. Entropy is mathematics quietly ruling the physical world. Now we arrive at the heart of the matter. If entropy is just counting microstates, why does it always increase? Why doesn't the universe occasionally get lucky and reverse it? Suppose you start with a low entropy state. There are very few microstates that look like this. Now let the system evolve freely. Almost every possible microscopic motion leads toward states with more microstates, states that are statistically dominant. The chance of accidentally returning to the original low entropy state is not zero, but it is so small that it will never occur within the lifetime of the universe. This is why entropy increase feels absolute, not because it is forbidden, but because reversal is practically impossible. The second law is not a force. This is crucial. Entropy does not push systems forward. There is no entropy field. The second law is a statement about likelihood. It says, given enough particles, the most probable outcome always wins. This is why the law works, for engines, for stars, for galaxies, for the entire universe. Why you cannot destroy entropy. You may reduce entropy locally, but when you do, you must increase entropy elsewhere by a larger amount. This is why refrigerators heat the room, computers produce waste heat, living organisms dump entropy into their environment. The universe always balances the books. A profound pause. At this point, we have learned something unsettling. Entropy is not a technological problem. It is not an engineering challenge. It is built into the statistics of reality. And now the real depth begins. At the microscopic level, something remarkable is true. If you take the fundamental equations of physics, Newton's laws, Maxwell's equations, Schrödinger's equation, almost all of them work equally well forward and backward in time. If time suddenly reversed, electrons would still obey quantum mechanics, planets would still obey gravity, atoms would still collide according to the same rules. And yet, a broken glass would not reassemble. Heat would not flow from cold to hot. Smoke would not crawl back into a cigarette. So where does irreversibility come from? Microscopic reversibility versus macroscopic irreversibility. At the level of individual particles, collisions are reversible. Dynamics are symmetric. But macroscopic systems involve 10 to the 23 particles, vast numbers of interactions, rapid loss of correlations. This leads to irreversibility by overwhelming statistics. Once microscopic information is spread across billions of degrees of freedom, retrieving it becomes physically impossible. Not difficult, impossible. This is why entropy gives time its arrow. James Clerk Maxwell and the first challenge. In the 19th century, James Clerk Maxwell proposed a thought experiment that shook physics. A tiny being, later called Maxwell's demon, could supposedly observe individual molecules, open and close a door between two chambers, let fast molecules go one way, slow ones the other. In principle, this could decrease entropy, create a temperature difference without work, violate the second law. For decades, physicists were confused. The equations allowed it, reality did not. The resolution came much later, in the 20th century. Entropy was not just about energy, it was about information. Szilard, Landauer, and the cost of knowing. In 1929, Leo Szilard realized something profound. To reduce entropy, the demon must acquire information, and information is physical. Later, Rolf Landauer made this precise. Erasing one bit of information necessarily produces entropy. This is known as Landauer's principle. It states that computation itself is not costly, but forgetting is. Every time information is erased, heat must be released. Entropy must increase. This is why computers heat up. Memory has a thermodynamic cost. Perfect control of a system is impossible. Entropy cannot be destroyed because information cannot be erased for free. This means the second law is not about heat alone. It is about loss of information, spreading of correlations, the impossibility of perfect knowledge. Entropy increase is the universe forgetting details. At absolute zero, a system occupies its lowest possible energy state. Thermal motion vanishes. Entropy reaches a minimum. But here is the critical point. The minimum entropy is not zero in general. Quantum mechanics forbids perfect stillness. The third law of thermodynamics. The third law states, as temperature approaches absolute zero, entropy approaches a constant minimum. This minimum depends on quantum degeneracy, ground state structure, and zero-point energy. To reach absolute zero would require infinite steps, infinite time, perfect isolation, which is why absolute zero is unattainable, and therefore minimum entropy is unreachable. This is not experimental failure, it is fundamental. Walther Nernst and the quantum limit. Walther Nernst formulated the third law while studying chemical reactions at low temperatures. What he discovered was not chemistry, but a deep constraint imposed by quantum physics. Quantum uncertainty ensures residual motion, residual entropy, residual ignorance. Entropy survives even at the coldest edge of reality. In classical physics, entropy comes from ignorance. In principle, perfect knowledge could reduce it. In quantum physics, probability is not ignorance. It is fundamental. This changes everything. Von Neumann entropy. In quantum mechanics, entropy is defined as S equals negative K trig of P ln P, where P is the density matrix. Entropy measures quantum uncertainty. Even with complete knowledge, outcomes are probabilistic, correlations are unavoidable. Entanglement spreads entropy. Entanglement and irreversibility. When particles become entangled, information is shared non-locally. Subsystems lose independent descriptions. Once entanglement spreads into the environment, reversal becomes impossible. Entropy increases irreversibly. This is why quantum measurements are irreversible. Decoherence creates classical reality. Entropy grows even in isolated quantum systems. Now we reach one of the most astonishing discoveries in physics. Black holes have entropy. This was shocking. Bekenstein and Hawking. In the 1970s, Jacob Bekenstein proposed that black holes must have entropy, otherwise the second law would be violated. Soon after, Stephen Hawking showed that black holes emit radiation, they have a temperature, they obey thermodynamic laws. Black hole entropy is proportional to surface area, not volume. This suggests something radical. Information is stored on boundaries. Why this matters? Black holes represent the maximum entropy possible for a given region of space, the ultimate limit of information storage, the deepest connection between gravity, quantum mechanics, and thermodynamics. Entropy is not just unavoidable, it is fundamental to space-time itself. Here lies the deepest mystery. If entropy always increases, why did the universe begin in such a low entropy state? Physicist Roger Penrose calculated that the initial entropy of the universe was extraordinarily low. The probability of such a state is unimaginably small, and yet it happened. This is why time has a direction, structure can form, life is possible. Entropy increase explains the future, but not the beginning. An open problem. Why the universe started ordered is still unknown. Possibilities include cosmological boundary conditions, inflationary dynamics, new laws beyond current physics. What is clear is this. The second law depends on the universe starting special. Entropy cannot be destroyed because it began low once.
Entropy is not pessimistic. It is not decay. It is accounting. It tells us why limits exist, why perfection is unreachable, why time flows, why complexity is temporary, why order must be paid for. The universe never forbids creation, it only demands payment, in entropy. References: Ludwig Boltzmann, Lectures on Gas Theory; Clausius, Original Formulation of Entropy, 1865; Szilard, 1929, On the Decrease of Entropy in a Thermodynamic System; Landauer, 1961, Irreversibility and Heat Generation in the Computing Process. At the deepest accepted level, entropy increase is not a postulate. It is a derived consequence of statistical mechanics. The second law emerges when three ingredients are present: large numbers of degrees of freedom, coarse-grained descriptions, and typicality of microstates. Let's unpack this precisely. In classical mechanics, the full state of a system is represented as a point in phase space: positions, qi, momenta, pi. For n particles, phase space has 6n dimensions. Liouville's theorem states the volume of phase space is conserved under time evolution. This seems to contradict entropy increase. So where does entropy come from? Entropy does not arise from exact microscopic dynamics. It arises when we group microstates into macrostates, ignore fine-grained correlations, describe systems with limited resolution. This is called coarse graining. As time evolves, the system's phase space distribution stretches and folds. Fine details become inaccessible. Coarse-grained volume increases. Entropy increase is, therefore, a consequence of limited observability combined with chaotic dynamics. Without coarse graining, entropy would not increase, but coarse graining is unavoidable in any physical measurement. Boltzmann's H-theorem. Boltzmann attempted to derive the second law using his famous H-theorem. Under assumptions of molecular chaos, Stach-Zal-Ansatz, weak correlations at collisions, he showed that a quantity related to entropy monotonically increased. This was revolutionary and controversial. Loschmidt objected, if microscopic laws are reversible, entropy increase cannot be inevitable. Boltzmann's response, entropy increase is not inevitable, it is overwhelmingly probable. This probabilistic nature is the key. A common advanced objection is the Poincaré recurrence theorem. It states, a finite, isolated system will eventually return arbitrarily close to its initial state. Doesn't this mean entropy can decrease? Technically, yes. Physically, no.
Why recurrence is physically irrelevant. For macroscopic systems, recurrence times exceed 10 to the 10 to the 23 years, longer than the lifetime of the universe, longer than proton decay timescales. More importantly, the system must remain perfectly isolated. No decoherence, no environmental coupling. Such conditions never exist in reality. Thus, recurrence does not violate the second law in any operational sense. Entropy destruction is not forbidden mathematically, it is forbidden physically. Most real systems are not in equilibrium. They constantly exchange energy, exchange matter, exchange information. Modern thermodynamics focuses on entropy production, not just entropy increase. Local entropy balance equation. In non-equilibrium thermodynamics, ds dt equals phi plus sigma, where phi is entropy flow to the environment and sigma is internal entropy production. Internal entropy production is always non-negative. You may export entropy, but you cannot make sigma negative. This is a strict inequality, not statistical. In the last 30 years, physicists discovered something remarkable. On very small scales, entropy can temporarily decrease. This is described by Jarzynski equality, Crookes fluctuation theorem. But these do not violate the second law. They refine it. They show small violations occur, but large violations are exponentially suppressed. In the macroscopic limit,
the second law becomes absolute. In modern physics, entropy is treated as a resource, like energy. Quantum information theory formalizes this. Entropy and unitarity. Quantum evolution is unitary. Information is conserved globally. So, why does entropy increase? Because
subsystems entangle with environments. Reduced density matrices lose purity. Entropy increases locally. This is known as environment-induced decoherence. Entropy increase reflects loss of accessible information, not loss of total information. Quantum information theory proves quantum information cannot be deleted. It can only be transferred, delocalized, thermalized. This is a deep reason entropy cannot be destroyed. Erasure simply means hiding information in inaccessible degrees of freedom. The most extreme test of entropy conservation occurs near black holes. Generalized second law, GSL. The GSL states S outside plus S black hole greater than constant. Even when matter falls into a black hole, total entropy still increases. This law survives Hawking radiation, black hole evaporation, quantum corrections. No known physical process violates it. Holography and entropy bounds. Modern theories suggest maximum entropy in a region scales with surface area, not volume. This leads to Bekenstein bound, holographic principle, ADS-CFT correspondence. Entropy appears to be a property of space-time geometry itself. We can now answer the question precisely. Entropy cannot be destroyed because microscopic dynamics spread correlations irreversibly. Information cannot be erased without physical cost. Quantum entanglement delocalizes information. Coarse graining is unavoidable. Entropy production is strictly non-negative. Space-time itself enforces entropy bounds. This is not a technological limitation. It is not a human limitation. It is a structural property of physical law. In advanced physics, entropy is inseparable from measurement, not consciousness, physical measurement. Any measurement requires a measuring device, interaction with the system, amplification to macroscopic degrees of freedom. This process is thermodynamically irreversible. When a measurement is performed, the system becomes entangled with the apparatus. The apparatus becomes entangled with the environment. Information spreads into inaccessible degrees of freedom. This creates entropy even if the quantum evolution is unitary. No energy is dissipated intentionally. Thus, measurement itself produces entropy. This is why quantum measurement cannot be reversed. Undoing a measurement is physically impossible. Entropy increase accompanies knowledge acquisition. Von Neumann formalized this using the measurement chain: system, apparatus, environment. Once information reaches the environment, decoherence occurs. Phase information is lost. Entropy becomes effectively permanent. Entropy cannot be destroyed because measurement cannot be undone. A common misconception is that entropy increase is subjective. It is not. Coarse graining is not a human choice. It is enforced by physics. Finite resolution as a physical constraint. All physical interactions have finite energy, finite bandwidth, finite resolution. This means infinite precision states cannot be prepared. Exact microstates cannot be tracked. Fine-grained correlations are lost immediately. Even an idealized observer embedded in the universe cannot escape coarse graining, cannot avoid entropy production. Thus, entropy increase is observer independent. It arises from physical limits, not ignorance. Entropy in ordinary matter is well understood. Entropy in gravity is not. This is one of the deepest unsolved problems in physics. Why gravity is special? Gravitational systems behave oppositely to ordinary systems. Gas spreads, higher entropy. Matter clumps gravitationally, also higher entropy. This seems contradictory, but it is not. Penrose's gravitational entropy idea. Roger Penrose proposed that smooth spacetime has low gravitational entropy.
Clumped spacetime, black holes, has high gravitational entropy. In this view, the early universe was smooth, low entropy. Structure formation increases entropy. Black holes dominate the entropy budget of the universe. This suggests most entropy in the universe is gravitational, not thermal. Physics does not allow arbitrary entropy. There are upper bounds. Bekenstein bound. For a region of radius r and energy E, S is less than 2 pi KER over h bar c. This means you cannot pack infinite information into finite space. Entropy has geometric limits. If entropy could be destroyed, entropy bounds could be violated, information density could become infinite, spacetime would become inconsistent. Entropy conservation is required for causality, stability of spacetime, consistency of quantum gravity. Does entropy define time, or does time define entropy? This is still debated. Two competing views. View 1, entropy creates time. Time's arrow emerges from entropy increase. Without entropy gradients, time has no direction. View 2, time is fundamental. Entropy increase occurs within time. Time exists independently of thermodynamics. Modern physics has not resolved this. What is clear, without entropy increase, the concept of past and future collapses. Entropy does not stop increasing. It defines the ultimate fate of the universe. Heat death revisited, scientifically. Heat death does not mean maximum temperature, destruction of structure instantly. It means no free energy gradients, no work can be extracted, maximum entropy under cosmological constraints. Stars burn out, black holes evaporate, information becomes maximally diluted. Entropy is not destroyed, it approaches its maximum allowed value. Can new physics violate the second law? This is a serious research question. Candidates include quantum gravity, closed time-like curves, exotic space-time topologies. So far, no experimental violation exists. All proposed violations reintroduce entropy elsewhere. The generalized second law survives every test. This makes entropy one of the most robust principles in physics.
At this depth, entropy looks less like a law and more like a consistency condition. Any physical theory must respect entropy bounds, preserve generalized entropy, prevent information destruction. Otherwise, predictions become inconsistent, causality breaks down, observables lose meaning. Entropy is a gatekeeper of physical law. Entropy cannot be destroyed because information cannot be erased, correlations cannot be unscrambled, measurement cannot be reversed, quantum entanglement cannot be undone. Spacetime enforces entropy bounds. Probability overwhelmingly favors entropy growth. This is not pessimism, it is structure. Entropy is what makes time directional, computation costly, life temporary, physics consistent. Despite everything, entropy remains unfinished science. Open problems include defining gravitational entropy rigorously, explaining the universe's initial low entropy, connecting entropy to quantum spacetime, understanding entropy in emergent gravity, reconciling unitarity with macroscopic irreversibility. Entropy is not the end of physics, it is one of its deepest entrances.